problems, and there is a whole field dedicated to neurosymbolic AI. And another way that logic and machine learning are kind of coming together is in the field of verification, testing, analysis, and security of ML systems. So that's the context for today's workshop, today's session. And the first speaker, it's my pleasure to introduce Professor Pedro Domingos from the University of Washington, Seattle. If you are in the broader AI field and neurosymbolic AI in general, Pedro needs no introduction, but I'll go ahead and give one anyways. He, as I said, he's a professor at Washington, Seattle, and author of the book, The Master Algorithm. He has won many awards for his research, AAAI Fellowship, SIG-KDD Innovation Award, and many other awards. So without further ado, Pedro, the floor is yours. Please.
Thank you. So I'm going to talk about unifying logical and statistical AI using Markov Logic. And here's the motivation. Intelligent systems have to deal with the complexity and uncertainty with the real world. And to deal with complexity, we have first order logic. To deal with uncertainty, we have probability. But the problem is that we need to combine the two. And that's what this talk is about, is how do we combine first order logic and probability, and then how do we learn and reason efficiently in the combined representation. And here's the basic idea. A logical knowledge base can be seen as a set of hard constraints on the set of possible worlds. If you violate even one constraint, the world becomes impossible. And that's what makes logic so brittle and hard to apply to the real world. So let's do the following. Let's make the formulas soft constraints instead of hard constraints, such that when a world violates a formula, it just becomes less probable, not impossible. And so, the more formulas a world violates, the less likely it becomes. And we'll give each formula a weight that reflects how strongly we believe in it. So if a formula with a higher weight is a stronger constraint, and you pay a bigger penalty for violating it. And then the probability of a state of the world is just a normalized and exponentiated sum of the weights of the formulas that it satisfies. So that's the intuition. Here's a slightly more formal definition. A Markov logic network, or MLN for short, is a set of pairs FW, where F is a formula in standard, completely standard first order logic, and W is a real number, positive or negative, or even infinite for hard constraints. And now together, that's the syntax. The semantics is the following, is that together with a set of constants representing the entities in the world, an MLN defines a Markov network, an undirected graphical model, as follows. The Markov network has one node for each grounding of each predicate in the MLN with constants, and one feature for each grounding of each formula in the MLN with the corresponding weight. Now that's a bit of a mouthful, so let's look at a simple example that will hopefully make things clear. And this is, a well-known example of social networks and the influence of social networks on people's smoking habits. So here are two sentences in natural language. Smoking causes cancer, and friends have similar smoking habits. And we can turn them into logic as follows. For every X, smokes X implies cancer X. And for every XY, friends XY implies that smokes X is equivalent to smokes Y. Now this is simple, but there's a problem with it, which is that those two sentences in English were true, and these two sentences in logic are false, because not everyone who smokes gets cancer, and not all pairs of friends have similar smoking habits. What we would like to do is turn this into the statistical regularities that they really are, and that's what we do by assigning weights to these formulas and turning this into an MLN. So this is a very simple MLN. Now, what does it mean? Let's suppose that we have two objects in the world, Alice and Bob, very small society. So now what is the recipe? Is I'm going to have one node in my Markov network, one Boolean random variable for every grounding of every predicate with both of these constants. So there's smokes Anna, smokes Bob, cancer Anna, cancer Bob. Each of these is just a Boolean variable. For example, smokes Anna is true if Anna smokes and false if she doesn't. And then similarly for friends, friends Anna Bob, friends Bob Anna, because of course friendship is not necessarily symmetric, and friends Anna Anna and friends Bob Bob, which maybe has to do with their self-esteem. So now we just have a bunch of Boolean random variables. And now the Markov network is going to have an edge, an undirected edge between any two variables that are directly dependent on each other, which means any two ground predicates that appear together in the same formula. So for example, we're going to have an edge between Cancer Anna and Smokes Anna. And now we're going to have a three-way clique for each grounding of the second formula. So for example, there's one between friends AB, Smokes A, and Smokes B, and so on. So now we just have a Markov network. And what is the probability distribution that this represents? Well, the probability of a state of the world, meaning an assignment of truth values to those Boolean variables, is just the normalized exponentiated sum over the formulas of the weight of the formula times the number of true groundings of the formula in that assignment. So a formula that has more true groundings and the large positive weight will contribute more, and so on. And notice something very important here, which is that an MLN does not just represent a single distribution. It actually represents a whole family of distributions. When you ground it with different domains, you get different distributions. And this is part of what makes this very powerful and useful, is that an MLN in some sense is actually a program for constructing probability distributions with all the advantages that programs have over doing things in assembly code. And you might also be thinking that, well, this is interesting, but it's not very practical because it's going to, the MLN will blow up when you ground it. And in fact, a good chunk of this is going to be about how we solve that problem. But a very simple thing you can do right off the bat that's very helpful is just to have typed variables and constants. So for example, if you have something like works for XY, X only needs to be instantiated with people and Y with with organizations. Also, what I'm going to talk about here is actually a subset of MLNs to just keep things simple. But Markov logic has all the features of first-order logic, including functions, existential quantifiers, and it can specify probability distributions over infinite and continuous domains, and so on. So how does Markov logic relate to first-order logic? Well, there's a very nice relationship, which is that if you let all the weights go to infinity, then you pay an infinite penalty for violating a formula. And so this just becomes first-order logic. So there's a theorem that says all entailment queries in first-order logic can be answered by computing conditional probabilities in an MLN, with infinite weights. But of course, the interesting case is when the weights are finite. And what can we say there? We can say something very interesting, which is that if I have a satisfiable knowledge base with all positive weights, then the satisfying assignments are the modes of the distribution. So the worlds that first-order logic likes are still there. They've just become the modes of the distribution. And then as we move away from them, the probability decays gracefully as opposed to falling off a cliff. But most important, of course, is the case where the knowledge base is not satisfiable, when there are contradictions. And in standard first-order logic, when there's a contradiction in the knowledge base, pigs fly and everything falls apart, which makes it very hard to build very large knowledge bases or collectively constructed knowledge bases like the semantic web and so on. In Markov logic, there's no problem at all. If you have a contradiction, then you just sum the weights on either side and you get a probability that comes out of that. What about the relation to the statistical models that we use in machine learning? Well, again, essentially all the major classes of statistical models that are widely used are simple special cases of Markov logic. You can typically specify them with just a couple of formulas. Things like graphical models, including Markov and Bayesian networks, maximum entropy models, logistic regression, hidden Markov models, conditional random fields, and in particular these days, very importantly, many deep architectures like deep Boltzmann machines, deep belief networks, and so on, are also special cases of Markov logic. And these are all special cases that are obtained by making the predicates be zero arity. So that you actually do not have dependencies between objects. All that you have is independent objects. And the nice thing about Markov logic is that it allows those dependencies via predicates like friends x, y. And so you can have much richer classes of distributions. So this is all very nice, but it's not very useful if we can't do inference in this language. So how do you do inference in Markov logic? Well, inference is computing the probability of a query given evidence and an MLN and a set of constants. And this is the same as computing the probability of an MLN where the evidence has been compiled out, just as in ordinary graphical models. And of course, as we saw, an MLN and a set of constants defines a Markov network. So at the end of the day, inference boils down to computing the probability of a query in a Markov network. And this can be done using any probabilistic inference algorithm you like, including MCMC, belief propagation, and so on. But there is, of course, a huge problem, which is that the ground Markov network in all but the smallest domains is going to be too large because it's going to be exponential in the closed arity. So we need something else. So what might that something else be? Well, what we can do here, as we're going to do every step of the way, is port over ideas from first order logic, in particular lifted inference. Right? The same thing that Robinson did for logic, we're going to do for probabilistic inference here. So what does, and the benefit of lifted inference is that now you can reason at the level of whole sets of objects at once, potentially even reason over infinite objects in finite time. So how do we do this? Here's just a high level, very high level sketch. The probability of a query is really just the sum over the worlds where the query holds of the probability of the world. And if this wasn't exponential, we'd be done. Now, of course it is, so what do we do? Well, there's two steps here. One is that if a world can be divided into independent subworlds, then its probability is just the product over the subworlds of the probability of each subworld. Number one. Number two, this gets rid of one of the exponentials. There's a double exponential going on here, and this gets rid of one of them. And the other one is the following, is that if I can group the subworlds into kinds that have the same probability distribution, then the probability of a world is just the product over the kinds, not the subworlds, of the probability of any subworld in the kind raised to the number of worlds in the kind. This is very powerful because now this gets rid of the other exponential. And then now finally I actually have something that is tractable, on a good day, as we'll see. Now, of course, in most domains, there aren't independent subworlds because otherwise, why would we have, a joint model for them? But the point is that if you condition, the more variables you condition on, the more random variables, the more, ground predicates you condition, the more independence you get. So by combining these two things, on a good day, you'll actually get something that is pretty efficient. Here's a small example to illustrate this. So going back to the smokes and to the friends and smokers example, here's our MLN. And now let's suppose that I'm going to condition on smokes X, right? Meaning I know whether or not Anna smokes and I know whether or not Bob smokes. Well, this actually makes, all of these, it makes smokes Anna and smokes Bob disappear, of course, and also all the edges involving them. So now we actually get something much simpler. We just get, in this simple case, a bunch of independent variables. But now further, let's say that we know that either Alice and Bob both smoke or neither does, right? Then actually, these 6 nodes actually just have 2 different distributions. There's one for all the friends XY nodes, the green one here, and there's one for the red nodes. And so if you look at the bottom of the screen here, computing this long train of conditional of this joint probability just becomes the probability of cancer squared times the probability of friends XY to the 4th, right? So now actually this can be computed very, very efficiently, right? Now, of course, this is on a good day. On a bad day, for example, Anna and Bob have different smoking habits, so you don't get as much of a compression. You don't get as much of a reduction. You typically still get some, right? So at one extreme, you get something that is the size of just the original MLN. At the other extreme, you get no benefit. And usually you're somewhere in between. And in fact, I'm going to that here, but you can do approximate lifting, which is very powerful because often at a small approximation cost, you get a huge reduction in inference complexity. So this is embodied in a procedure that we call probabilistic theory improving. And probabilistic theory improving is very nice because it has almost all the major types of inference that we have to do in AI as special cases, as illustrated in this figure here. So if you look at the bottom left corner, you have traditional propositional theory improving, which of course is equivalent to SAT. And now there's 3 ways in which you can extend this. One is by counting. You want to count the number of satisfying assignments. So now you have model counting. Another one is by weighting. So you have, the weighted SAT problem. And the one is by lifting to first order level. And each of these now corresponds to interesting problems. So for example, the weighted case is the same as MPE inference, finding the most probable explanation or the most probable state in probabilistic inference. The weighted The weighted model counting problem is equivalent to standard probabilistic inference, like what people typically do graphical models. And now, of course, there's lifted versions of all of these. And at the top right corner there, you have the full-blown probabilistic improving, which is really just lifted weighted model counting. So with this one procedure, and we have an implementation of this that I will point to later. You can actually do all of these things, all the way from just standard propositional, from basic SAT to all kinds of probabilistic and first-order inference. And these are really, like what we use at the bottom left corner there. You could use different things, but it's really just DPLL. And so what we have here are successive extensions of DPLL all the way to lifted weighted model counting, which we call probabilistic improving, because that's what it amounts to. Okay, so what about learning? So briefly, in learning, data is no longer a single table as in ordinary machine learning, but is a full relational database, right? You can have any number of relations. And that's what we want, because that's what the real world has. The real world isn't just one table that we have to somehow, hack everything into. And I'm going to make the closed world assumption here for simplicity. It's not always appropriate. If you don't make the closed world assumption, then you need EM versions of the algorithms that I'm going to describe here, which we also have. And now, of course, there's learning parameters, i.e. the weights of the formulas, which can be done generatively or discriminatively. And there's learning structure, which is learning the formulas. So to learn parameters, as it turned, we thought this was going to be a hellishly difficult problem, because now the data is not IID, so maximum likelihood, basically falls apart. But actually it turns out to not be the case. Learning is at some level just as simple as before. We can use gradient descent. It's a convex problem. There's no local maxima. The gradient with respect to each weight actually has a very simple and intuitive form. The gradient of the log likelihood with respect to a weight is just the number of true groundings of the corresponding clause in the data minus the expected number according to the model. So if a clause is true more often than the model says, then its weight needs to go up. If it's true less often, its weight. If it's true more often, the weight needs to go down, etc. And when they all line up, then you're done and you have the maximum likelihood solution. The only snag, of course, and there has to be a snag, is that to compute the expected number of true groundings, you need inference. You need an inference, itself can be expensive, of course, and you need to do this at each step of gradient descent. So most of the time, this is going to be too expensive. So what can we do? Well, we can change the subject, right? If you can't solve the problem, solve a simpler problem that hopefully is not too different from the real one. And here there's a natural candidate, which is something called pseudo-likelihood. Pseudo-likelihood is just the product over all the random variables of the product of each variable given its neighbors in the Markov network. And the beautiful thing about this is that it does not require inference. And it's also a consistent estimator, so it's reasonably statistically well behaved. It's widely used, but of course it doesn't always work very well. If what you need at inference time is short chains of inference, this will work well because that's what it was optimized for. But if you need long chains of inference, it probably won't because it wasn't optimized for that. So what can you do in that case? Well, in that case, you can do discriminative learning, and in machine learning, typically you always wind up doing discriminative learning at the end of the day because that's what gives the best results. So it's a good thing to do in its own right. And what is the idea here is that if I know in advance which variables I'm going to be querying and which ones are evidence, I can just optimize the conditional probability of the query given the evidence instead of the whole joint distribution, which is a much harder thing. And everything, is pretty much the same as before, except with conditional probabilities now. The big gain here is that what makes inference hard is that the probability distributions are typically highly multimodal, right? And then I have to sum over those modes. But as I add evidence, most of those modes disappear. In fact, often all but one disappear. And so now instead of doing this exponential sum over all the states, I can just find the peak, the most probable state, and use the counts in that state as my expected counts. And this is something that is very standard. In fact, you could say it is the standard in practice in probabilistic in most domains. And we can use that here. So there's many different algorithms to do this, but A simple one is what is called the structured perceptron, or an extension of the structured perceptron, which was originally introduced by Mike Collins for training hidden Markov models discriminatively. So of course, the restriction there is that you assume the network is a linear chain, and now you just do the following. You initialize all weights at 0, and then you do the following some fixed number of times. You use the Viterbi algorithm to infer the most probable state of the hidden variables given the observable ones. For example, what you said given the phonemes that were heard in speech recognition. And then you count things in that state that you inferred, and the difference between those counts and the counts in the data is your gradient. You multiply that by a learning rate, and you add to the weights. And then you just return the average of this over all the steps. Why the average and not the last result? Well, it's both theoretically predicted and empirically verified that you get better generalization this way. And it's not surprising because it helps to combat overfitting. Now, of course, what we want to do is inference over any MLN, but we can do that by extending this algorithm in a very simple way, which is that instead of Viterbi, we just use PTP. In particular, we use the maximizing the MPE version of probabilistic improving, and the rest of the algorithm can stay pretty much the same. Okay, so that's your basic weight learning. What about structural learning, right? We don't just want to learn weights for predefined formulas. We want to be able to discover those formulas from data if we can. Well, if you think about it, this is both a generalization of the problem of feature induction in Markov networks and also of inductive logic programming. And you could use, in principle, any such ILP, meaning inductive logic programming approach here, but with a couple of differences. One is that in ILP, of course, you just induce horn clauses, and here we want to induce any clauses. And also in ILP, usually your evaluation function is some form of accuracy or information gain. But here we're learning a probabilistic model, so it should be a likelihood or a Bayesian posterior or something like that. And indeed, we can do this fairly straightforwardly. There is, of course, a problem, which is that in order to do this, we need to learn weights for every candidate formula. So our search process is going to propose candidate clauses. Every time we have a candidate, we need to relearn the weights in principle for all the formulas, right? Because they're all tied together. And well, and doing this at every step of a large search could, and this itself is expensive, could be a problem. As it turns out, surprisingly, this is not the bottleneck. If you do a couple of very simple things, namely, if you initialize the weights at the current ones instead of starting from scratch, and if you use a fast optimizer like a Newton, quasi-Newton, LBFGS type optimizer, you typically converge in just 1 or 2 iterations. So the bottleneck, interestingly, turns out to be something else. It's counting clause groundings. As it turns out, counting the true groundings of a clause in a database is already an NP complete problem. And in weight learning we only had to do that once at the beginning, but now we have to constantly do it when we propose clauses. So this turns out to be the bottleneck. But again, we can get around this bottleneck just by being minimally intelligent. And there's a number of things we can do, but the most important one is just to subsample, right? If I have a clause with 1 million groundings, I actually don't need to count over all of them. I can just randomly sample them using something like Karp-Luby, and then extrapolate the number of true groundings that I found to the number of true groundings in the whole database. And with this, we can actually learn structure for MLNs with roughly the same efficiency that you can learn features for Markov networks or learn logic programs, which is not blindingly fast, not super scalable. We'll have a little bit more to say about making this truly industrial strength in just a second, but is actually good enough for a lot of applications. And in terms of unifying these two things, it's basically reaching the goal. So of course, in structural learning, to now get more precise, you need to specify a number of things. The first one is the initial state, and the default is just unit clauses, right? Basically assuming that they're all independent. A much more interesting alternative, however, is to initialize with a hand-coded knowledge base. This is how we typically use MLNs. We actually start by getting knowledge from people or extracting it from tests or whatever. And then we have a bunch of formulas which are useful, but probably need repaired and extended. So we can initialize with a hand-coded knowledge base. And now, of course, we need search operators. The obvious ones are adding and removing literals. Another very useful one to have is flipping the sign of a literal. Because when people write formulas, they often get the formula roughly right, but they put the implication in the wrong direction. And so flipping a sign helps with that. And of course, it helps. You could do that by adding and moving a literal, but it, you know, flipping it gets over a hump in the optimization landscape that otherwise would stop you. You need an evaluation function. The obvious one is pseudo-likelihood, of course, because it's efficient, but we have to combine that with some kind of structure prior to avoid learning, you know, as in graphical models, a completely connected graph. And so a very common one is to just penalize divergence from the prior hand-coded knowledge base. Every time that I want to modify the knowledge base, the increase in likelihood has to exceed the prior penalty. And you know, this is just as in graphical models and works quite well. And finally, of course, you need the search method. You know, a common one is beam search, which comes more from the Markov network side. Sorry, from the ILP side, shortest first from the Markov network side, and bottom up, genetic. You know, there's many different papers about how to do this, and you can pick your favorite method. So, are we done? Well, not really, because this is still not really scalable to the kinds of very large knowledge bases and models that we have today, and not truly industrial strength, right? It still needs a bunch of hand-holding for the inference, whatever form it takes. You know, you have to look under the hood, if you will. You can't just drive the car. So what can we do? Well, again, we're just going to take a page from, you know, classic AI, and we're going to look at tractable subsets, right? In the same way that people spent, well, actually, they're still doing this, right? But it started in the 70s, like looking at tractable subsets of first-order logic. We're going to look at tractable subsets of Markov logic. So here's one that we've introduced. It's called tractable Markov logic. And not surprisingly, it's a description logic type language. It's object-oriented. There's a class hierarchy, and there's a subpart hierarchy. And as long as the dependencies are mediated by that hierarchy, you can actually do inference in time that is linear in the number of rules and objects in the model. And in practice, it's actually even less than linear, because you just recompute the parts of the model that you need to when you have new evidence or a new query. And again, without going into the gory details, why is this possible? Well, here's a one slide explanation. The basic assumption that we make here, or there's two. One is that the probability of an object given a class is the product over its subparts of the probability of the subpart given the class. So the idea is that knowing the class of an object breaks it into independent subparts, which then in turn will have their classes, which will then break them up further, and so on, all the way to individual relations. And the other one is basically the mixture model hypothesis, is that the probability of something given a class is just the sum over the subclasses of the probability of that thing that we're interested in, given the subclass, times the probability of the subclass. Okay? And what these two assumptions bias is that now the structure of the computation is isomorphic to the structure of the knowledge base. Everywhere I have a class being broken into subclasses, I have a sum node, and everywhere I have an object being broken into subparts, I have a product node. And so there's no blow up at all. That's why it's linear. It's like the computation is a copy of the knowledge base of the MLN, so it takes the same amount of time, or as I mentioned before, you know, typically even less. And we've applied this to building a large web knowledge base, which we extracted from DBpedia, Yago, and Nell, all of them very well known web knowledge graphs or knowledge bases, if you will. It's by largest to our knowledge, by far to our knowledge, the largest first-order probabilistic system ever built. It has millions of objects and billions of parameters, and yet you can answer any query in this language exactly, not approximately, in sub-second time. So you can actually, you know, do this interactively. You can work with these models interactively. And of course, there have been many other applications of Markov logic as well. Probably the single biggest area is natural language processing, because of course it's a very natural match. There's a lot of structure and also a lot of ambiguity. But also things like social network analysis, robotics, computational biology, psych, the famous, you know, largest knowledge base ever built. Parts of it have been turned into MLNs using, you know, the ideas that I described here. Also personal assistants. The famous DARPA Kalo project that Siri came out of used Markov logic as its core inference engine. And MLNs have been widely used and researched in both academia and industry, not just at the big tech companies, but many others as well. So to summarize, I would say that it's fair to say that at this point we have largely succeeded in unifying logic and probability, and this is a problem that has preoccupied mathematicians and philosophers for a long time, and even been considered unsolvable by some. There's of course many different approaches to doing this, but the most general one, most powerful and most developed one is Markov logic, which is what I talked about here. And it essentially just consists of weighting your first order formulas and then turning them in that way into a log linear model, i.e. into a Markov network. There's a bunch of powerful inference and learning algorithms for it that we and many others have developed. And I think this can hopefully serve as a foundation for modern AI, where instead of just having to do a bunch of hacking to deal with real world problems, you can actually do things in a more principled way. There's of course much more still to do. If you'd like to learn more about Markov logic, I recommend reading this article that came out a couple of years ago in CACM. There's also a slightly older book, which you see here. It doesn't contain some of the things that I talked about here, but it's a pretty good introduction. There's also an open source implementation called Alchemy, and a website where you have not just Alchemy, but pointers to other open source implementations, data sets, papers, MLNs that you can use, modules that you can combine, and so on. And here's the URL. Thank you.
Thank you, Pedro, for a fantastic talk. So I'm going to clap for everybody. Thank you so much. All right, questions, please. Moshe, I think probably, yeah, go ahead.
So, let's look at the rule, all smokers get cancer.
Mm-hmm.
I can put some weight on it, but what I'd like to do is not to put a weight on it, but instead to say, this rule is true, but in a probabilistic way, which is for all smoker with independent probability, let's say, I don't know what it is, let's say 0.4, they get cancer.
Mm-hmm.
That's what I would like to say. So the rule will be universally true, but the probability will be on the implication. The implication will be probabilistic. Do you understand what I'm saying?
If I understand you correctly, that is what we're doing here. What I'm saying is that for every, take a very simple MLN, right? The MLN just says smokes X for all X with some weight, right? This is exactly the same as saying, every X smokes with an independent probability for each X. And this is actually crucial because if you're familiar with this history, Nielsen back in the 80s already proposed the maximum entropy version of logic, but the problem is that it took the whole formula as a unit. So this was not very useful, right? And in particular, didn't generalize the traditional probabilistic models. So what you said, if you have a formula in the MLN that says smokes X, what that does is that independently for every person, they smoke with that probability.
But where do I put where is the way for me to say the probability of cancer from smoking is alpha?
That's in the formula, that's in the weight of the second formula. So if you have a formula, smokes X implies cancer X, the weight of that formula is the probability of the implication. Now, to be very precise, it is not the probability that the consequent holds given the antecedent. It's a probability that the formula
But that's not what I want. That's not what I want, because then some people will not smoke, and that's another way to make it true. I want to say for each smoker, if this person smoke, then with probability alpha, this person gets cancer.
No, yes, so you can do that. So you can do the following. You tell me what you want that probability to be, and I will, give you the weight for the formulas that corresponds to.
I
so
see.
Any probability distribution that you want to put on this, I can give you the weights. Now you can ask the question, which people used to in the early days, right? Which was a very natural one, which is then why don't you just specify the model in terms of probabilities? Why weights, right? Because Bayesian networks, the model specified in terms of probabilities. The problem is that then you have an intractable problem right up front, which is to make sure that all those probabilities are consistent. I've just given you an enormous amount of flexibility in allowing any first-order logic statement to be there. And in fact, there are people that used to say that what we did was impossible, right? But now, and then those problems that those probabilities might not be consistent, right? You might be specifying a probability for one formula that is incompatible with the probability for another formula. If what you do is specify weights for the formulas, the weights can be anything you want, and you always get a well-defined probability, joint probability distribution out of it. But whatever the probability distribution is that you want, I can give you the weights. And in fact, this is the maximum entropy inference problem. Maximum entropy inference is precisely no more, no less than going from the probabilities of the formulas to the weights. Now, of course, in practice, the probabilities that we have are consistent when we learn from data because they're just the statistics that we measured on the data, right? But if you just wanted to specify probabilities out of your head, then you would risk, making them inconsistent.
Thank you.
Thank you, Pedro. Thank you, Moshe, for that question. Anybody else has a question?
Yes, may I ask something?
Please, please.
Yes, hi. So I have two questions. One is a simple question about the background and the relation between this. You said that the goal is to somehow combine logic and probability. So how would you what would you say is the relation with the fuzzy logic that had the same goal, if at all? And the second question is more applied. Is it really does it really, you talked about application. So is there a really interface with these kind of this technology with like procedures like that are applied nowadays in deep learning and so forth? Maybe I did not understand how this can be combined together, if at all.
Yeah.
Thank you.
So the relation to fuzzy logic is very simple. And it has two parts. One is that fuzzy logic is actually an alternative to graphical models. It's a propositional language. It's not a relational language. So I can imagine defining a first order version of a relational version of fuzzy logic in the same way that what we define here, you can think of as a relational version of graphical models, okay? So this is at a higher level, right? In the same way that first order logic is at a higher level than probabilistic logic. The second one, of course, is that these days people in AI don't do fuzzy logic because it's unsound, right? So, you could do things like that, but it would have the usual problems, okay? And again, it would be propositional at first order. So deep learning, I didn't go into the details of that, but it's actually fairly straightforward to take a lot of these deep learning models and express them in Markov logic. So in fact, when Jan LeCun first saw me describe Markov logic in a talk at NIPS, he actually said, oh, so what you have here is a language for defining Hamiltonians compactly, which is actually a very apt thing to say, right? So if you think of these, neural networks as optimizing an energy function, which is what a lot of them do, and again, that's how Jan likes to see it, then what MLN allows you to do is to define, any energy function that you want using first order logic. And by the way, I didn't get into that, but you can also define things, that are not just over Boolean domains, but over numeric ones, where a lot of these deep learning models are used. Okay? But then the benefit that you get is that, and this is a very big benefit, is that when you define these models in these deep models, if they're probabilistic, if they're just, energy-based models, then, you can optimize them and the two things at some level are equivalent. But if you actually want to compute probabilities with them, then you get killed by the partition function, right? Because the inference is highly intractable. In fact, Jeff Hinton famously said that he's lived his whole life under the shadow of the partition function. And what things like Markov logic, and in particular tractable Markov logic let you do, is actually they carve out a subset of this world where you actually can always find answers efficiently. And this subset, very importantly, is much larger than the subset of low tree width models, right? The problem with all of these deep networks is that they're high tree width. But the thing here that's very new and in some ways very surprising is that you can actually have high tree width models where the partition function is still tractable, and those are precisely what tractable Markov logic zeroes in on.
More questions? So, Pedro, I had a couple of questions. One is perhaps quite an obvious one, which is, in the solver domain, SAT solvers and model counting solvers, we constantly making progress and improving their efficiency and scalability. And I was wondering if these newer solvers could help your implementations in a meaningful way, because a couple of slides prior to your last slide, you mentioned that you already have very efficient inference, at least for the tractable version of. So how can this technology help you is kind of the broad question here.
I mean, it can certainly help us because, of course, the price that we paid in tractable Markov logic is that it's a restricted language, right? So there's a lot of things that we'd still like to say, right? And our preoccupation from day one actually has been to have a setup where if tomorrow you have a better, say, SAT solver, you can just plug it into here. If tomorrow you have a better ILP, induction algorithm, you should also be able to plug that in here, or take any of the pieces. What we want this to be, we want the people who use this to be able to use it without knowing what's under the hood. But we also want the people who work on the pieces under the hood to be able to plug in the new part without knowing the rest. And in particular, the probabilistic improving that I described here is based on DPLL. But there's versions of this that exist now. In fact, some of the early ones that we have were based on other SAT solvers. And again, the idea is that if tomorrow you have a better version of DPLL or a completely different SAT solver, you should be able to plug it in here and in some sense get the probability added for free. So if you come at this from the inference point of view, from the logical inference, the way to think about this, in fact, we had a paper in a book about uncertainty in the semantic web that the title was just add weights. You have your logical formalism, you have your logical inference engine, you add weights to it, and now instead you're doing probability computations. So that's the idea. Of course, depending on the exact SAT solver, this could be simpler or have some subtleties. But this has been done a number of times now. And again, the goal in the future is that every time that SAT solvers get better by an order of magnitude, inference in Markov logic should also get better by an order of magnitude.
Sounds great. I have one more question which had to do with NLP systems. I don't know enough about NLP, unfortunately, but you're aware of GPT-2 and GPT-3, right?
Mm-hmm.
So I'm assuming they're built on a different architecture than Markov logic networks. Would that be fair?
No, they are. So they're built on something called a transformer,
right.
and which is built on something called attention, and they use what is called contextual embedding, and these are all very interesting and powerful ideas.
So the question I have there is that they are susceptible to some very simple logical inference issues, these BERT-based systems. And would it be right to say that Markov logic network-based systems are not likely to be susceptible to those kind of logical issues? Or?
I mean, exactly, right? So,
Yeah.
but there's two sides to this. One is that, these models honestly are subject to all sorts of crap. Right. That Markov logic isn't, right? Nobody really knows what's going on there, right? It works some of the time it does ridiculous things and nobody really understands what's going on, right? So it's good that it works, right? On the other hand, it's not a very satisfying state of things. Markov logic, as I described here, doesn't have any of those problems by design, but is not scalable to the same degree, right? And of course, I showed you here one interesting subset called tractable Markov logic. We're actually currently working on a different one. So one way to think about this is like tractable Markov, there's like two major kinds, to oversimplify, of tractable languages. There's the logic programming type ones, and then there's the description logic type ones. Tractable Markov logic is a description logic version of Markov logic. We're currently working on a logic programming one, which we call tensor logic, which you can actually precisely specify all these models and the attention mechanisms and the modules that transform us, all the way up to GPT-3 are based on in this language, and then get the corresponding benefits. So this hasn't been published yet, but it's something that I'm very excited about.
Awesome. All right, thank you again for a great talk. It was a pleasure. Thanks a lot. Our next speaker is Vivek Srikumar. Vivek, can you please share your slides?
Yes.
Pedro unshares.
Yeah,
and